Hello there, and welcome. I'm so glad we can share this quiet moment together. Wherever you are, allow the night to gather softly around you. Picture the sky above, a vast, dark canvas waiting for the oldest stories to be told, not in a rush, but in the slow, patient unfolding of cosmic time. Tonight, we'll turn our gaze upward, much farther than the moon, to the points of light that have guided and fascinated us since the beginning. We're going to explore the spectacular, fiery life cycle of those distant suns, from the moment they awaken in a cloud of dust and gas to their final, quiet transformation. It is a story of magnificent power and incredible tenderness, a story that truly is, in a profound way, our story too. Let the scale of it all feel less overwhelming and more like a warm blanket. We belong to this universe, and there is a deep comfort in understanding the fabric from which we are made. As we drift through this cosmic journey, if you find this gentle wandering helps you settle your mind and ease your thoughts, please consider sharing a quiet like and a soft subscribe. It's the gentlest way to help others find their peace here too. Now, let your thoughts grow light. Let the stars be your guide into stillness. We'll begin together, unhurried and warm. Stars often feel, from where we lie under the sky, like eternal companions. They rise and set, season after season, so steadily that it is easy to believe they have always been there and always will be. Yet that calm impression is only a trick of perspective. Each star is a living process, not a fixed point. It has a childhood and a long middle age, and it someday comes to an end. It is born out of the tangled chaos of cold gas and dust, shines for millions or even billions of years, and then, in its own way, fades or explodes and yields its matter back to space. If you could watch the universe on a timescale far slower than a human life, you would see it breathing through these stellar changes. Regions of darkness would begin to glow, quiet clouds would crumple and ignite. A single star would swell, redden, and finally vanish into a brief, blinding flash or a soft, lingering ember. The sky above your head would no longer seem still. It would resemble a garden in slow motion, where new lights blossom as others fall away, and nothing remains unchanged. Tonight, we drift gently along one thread of that larger story, following the life of the stars through a handful of places where their transformations are especially clear. In imagination, we pass among vast nurseries where stars are just waking, through neighborhoods of more settled, middle-aged suns, and then out toward the heavy, swollen giants that are nearing their last breaths. We let ourselves move even farther, to the remnants left behind, when a brilliant star has already died and collapsed into something dark and strange. Step by quiet step, the illusion of eternity gives way to something more delicate, the sense that even the most distant lights are part of a cycle. One of the gentlest places to begin is in a cradle of young stars, not so very far away in galactic terms, the Orion Nebula. When you look up at the familiar pattern of Orion in the winter sky, you can trace his belt as 3 bright points in a row. Hanging from that belt is a short line the ancients imagined as a sword. The middle star in that sword is not really a star at all, but a smear of light, a cloud glowing softly in the dark. That is the Orion Nebula, a place where thousands of suns are in the process of being born, roughly 1,300 light-years from where you are resting. The Orion Nebula is just one of many stellar nurseries scattered through our galaxy. Some of these clouds are modest, spanning only a few light-years across. Others stretch for tens or even hundreds of light-years, veils of gas and dust spread so thinly that you could fly through them without feeling a thing. They drift in the galactic disk like slow tides, made mostly of hydrogen with traces of other elements mixed in. Gravity is patient. Small ripples in density, a passing shockwave from an older star's explosion, or the squeeze of nearby gas can coax parts of the cloud to begin collapsing. From far away, many of these nebulae are barely visible, dim smudges against deeper darkness. A few, like Orion, are bright enough that human eyes can pick them out without telescopes from a clear, dark place on Earth. That combination of closeness and size is one reason Orion has drawn astronomers' attention for centuries. It offers a nearby look at what a stellar nursery really is. Not an abstract idea, but a busy region where the raw material for stars and planets is actively being gathered and lit. When the Hubble Space Telescope lifted above Earth's atmosphere and turned its gaze toward Orion in the early 1990 seconds, it sent back images that made this region feel almost tangible. Instead of a vague mist, there were folds and filaments, curtains and caverns of color, reddish and bluish-violet hues, traced glowing hydrogen and other gases. Threaded among them were delicate streaks and knots that shimmered in an unexpected shade of green. That green light puzzled astronomers for a long time. When they split the nebula's glow into its component colors, the pattern of lines they saw did not match any element known on Earth. For a while, people even imagined that the nebula might contain a new substance, something they called nebulium, a gas that perhaps existed only in the depths of space and not on our planet at all. It was a reminder of how different conditions are in these regions, where densities are lower than any vacuum we can easily create in a laboratory. Eventually, with more careful measurements and a better understanding of how atoms behave in extremely thin, energized gas, the mystery softened. The strange green lines were not from a new element, but from ordinary oxygen atoms in a very unusual state, so rarefied and so gently excited that they could radiate in ways that are almost impossible to reproduce down here. Realizing this did more than clear up a single puzzle. It showed that what looks empty can still be full of subtle activity. In Orion and in other nebulae, the faint glow is a sign that starlight is slowly reshaping the gas around it, kicking electrons into higher energy levels and letting them fall again, releasing tiny packets of light. The colors we see are like a quiet code, telling us which atoms are present, how warm they are, and how the newborn stars are beginning to influence their surroundings. If you could float closer to the heart of the Orion Nebula, you would find that it is not just a pretty cloud, but a crowded neighborhood. Astronomers have identified thousands of young stars here, along with clumps of gas that have not quite ignited, and embryonic systems still wrapped in dusty cocoons. All of this richness is packed into a region only a few dozen light years wide, small compared with the galaxy, but enormous compared with anything in everyday life. The total mass gathered there is equivalent to many thousands of suns, all bound together in a loose, luminous complex that is still taking shape. Within this wider glow lies one of its most striking features, a compact star cluster known as the trapezium, or Theta 1 Orionis. If the nebula is a kind of cosmic cloud, then the trapezium is a cluster of brilliant sparks near its center. The stars here are extremely young on stellar timescales, only a few 100,000 years old. They have just recently emerged from their birth clouds, and they pour out light and wind with a kind of restless intensity. The cluster takes its name from the way its four brightest members form a small, uneven quadrilateral in the sky, like a tiny, crooked diamond. Those four main stars, are only the most obvious parts of the cluster. Around them are several other massive suns, some bound together in pairs, others apparently alone, all influencing each other through gravity and radiation. Each of the brightest trapezium stars is many times more massive than the Sun and far hotter. They radiate mostly in ultraviolet light, invisible to human eyes, but powerful enough to strip electrons from nearby atoms and to carve cavities in the surrounding gas. Where their influence is strongest, the nebula thins. Where it is gentler, delicate surfaces of gas and dust light up like the edges of clouds at sunset. Among these young powerhouses, one stands out. Theta 1 Orionis C is the most massive and luminous star in the trapezium, and in many ways, the main lantern of the entire nebula. It has a mass several tens of times that of the Sun, and its surface is tens of thousands of degrees hotter. Because of that, it shines hundreds of thousands of times more brightly than our star. The radiation streaming outward from this single object floods much of the Orion Nebula, sculpting it, heating it, and slowly pushing material away. Close to Theta 1 Orionis C, the space is relatively clear. The star's fierce stellar wind, a steady outpouring of charged particles, sweeps the thin gas aside, hollowing out a kind of bubble around it. Farther away, where the wind has slowed and encountered denser material, curtains and ridges of gas glow softly. Inside, some of these denser knots, smaller and gentler stars are forming, shielded for a time from the harshest radiation. The scene is both forceful and tender, powerful winds blowing cavities into the cloud, while in the sheltered pockets, new suns are quietly gathering themselves together. If you drift just a little farther, a few light years from the trapezium, another remarkable system comes into view, Theta 2 Orionis. It lies near a bright feature astronomers call the Orion Bar, a long, glowing ridge of hot gas where the intense light from the cluster meets cooler, denser material. For many years, this region was difficult to study in detail because thick dust blocked much of the visible light. The area appeared as a bright but somewhat hazy band, with only hints of the fine structures within it. With the arrival of the James Webb Space Telescope, looking in infrared wavelengths that can slip more easily through dust, this part of the nebula has opened up in new detail. Webb's images reveal ripples, pillars, and tiny, dark silhouettes, places where small clumps of gas and dust still resist the onslaught of radiation, and where future stars may yet be forming. Against this intricate background, Theta 2 Orionis stands out as a compact family of 3 stars bound together by gravity, circling a common center like dancers sharing the same slow music. The most massive of the Theta 2 stars is only slightly less extreme than the Great Lantern of the trapezium, still far heavier and brighter than the Sunday. Its companions, while less intense, are each several times the Sun's mass and thousands of times its brightness. Together, they contribute to the nebula's illumination and help shape the nearby gas, their combined winds and light, adding their own patterns to the Orion Bar. Yet, as astronomers have peered more closely into the Orion Nebula, with telescopes like Hubble and Webb, their attention has not rested only on the most dazzling stars. In the softer, redder light of infrared, another population emerges from behind the haze, small, dark shapes outlined against the glow, like seeds still wrapped in their shells. These are protoplanetary disks, thick, flattened swirls of gas and dust around very young stars. Stars so new that they have not yet fully settled into their long, steady phase of life. The James Webb Space Telescope, with its sensitive infrared eyes, has revealed many such objects, in the heart of the Orion Nebula. Where visible light mostly shows the bright gas and the hottest stars, Webb can peer into the cool, dusty regions and pick out the silhouettes of these disks. Astronomers have identified on the order of a couple of hundred of them, each one a tiny laboratory of planet formation. In the images, some look like dark ovals, with a bright star at their center. Others appear as small, comet-like shapes, their outer layers being gently eroded by nearby radiation. One of these young systems is known by a string of numbers Orion, 294 to 606. The name may sound dry, but the reality it represents is anything but. At the center of this object is a very young star, only about 1 million years old. Around it, a wide disk of gas and dust extends hundreds of times farther than the distance between Earth and the Sunday. Because this system is relatively close in cosmic terms, and because the nebula around it is so well studied, astronomers can make out some of its structure. The dense inner regions where material is slowly spiraling inward, and the more delicate outer parts where clumps and filaments hint at the first steps toward building planets. Given enough time, only a few million years by stellar standards, but an unimaginable stretch on a human timeline, the young star at the heart of Orion, 294 to 606, is expected to reach what astronomers call the main sequence. That is the long, stable stage when hydrogen in the star's core fuses steadily and its brightness and temperature remain relatively constant for a very long time. By then, much of the disk around it will have transformed. Some of its dust will have stuck together into pebbles, then boulders, then the solid cores of planets. Some of the gas will have been drawn into the star itself. Some will have been blown away. If everything unfolds the way it often does in such systems, a small family of planets will eventually circle that star, perhaps some rocky, some icy, some wrapped in deep atmospheres of gas. Around those planets, in turn, there may be moons, small worlds lighting up the night skies of one another. From the surface of such a world, if it has a surface at all, the view would be very different from the sky you know. The surrounding nebula would still be glowing, a soft, multicolored curtain stretched across the darkness. Nearby, young stars would shine more thickly than they do from Earth, and their combined light might make the nights feel like a permanent, dim twilight. You could imagine standing there, looking up. Instead of a dark sky sprinkled with isolated points, you would see a luminous mist, streaked with brighter knots and bands where the gas is denser. Now and then, a wave of brighter emission might drift into view as a shock front or a swirl of hot gas moves through the region, painting half the sky in gentle color. In reality, these changes would unfold slowly over many lifetimes, but to the mind, they can be gathered together into a single, shifting, living sky. Stepping back again, to the scale of the nebula as a whole, the space between these young systems is far from empty. The central region of the Orion Nebula is filled with a sea of ionized hydrogen, atoms that have lost their electrons under the assault of intense ultraviolet radiation from the massive stars. This energized gas forms what astronomers call an H2 region, a hot bubble where the temperature can climb to around 10,000 degrees. Closer to the center, where the light is strongest, the gas is more highly ionized and brighter. Farther out, as the radiation weakens, the gas cools and recombines, and the glow softens. Within this glowing bubble, nothing is truly still. The pressure of hot gas in the center pushes outward, while cooler, denser material presses back from outside. Stellar winds from massive stars plow through the region, sending outflows in different directions. Where these flows collide, they set up great currents and eddies. enormous whirlpools of gas that can span distances larger than the orbit of all the planets in our solar system combined. Some of these streams move at tens of kilometers each second. You could never feel such motions directly. If you were there, the gas is too thin. But you would see their traces in the shapes of the nebula, arcs, loops, and ripples, slowly carving and reshaping the cloud. Threaded through this hot medium, astronomers find something more delicate, thin filaments of cooler molecular gas, made mostly of hydrogen, bound into simple molecules, sometimes laced with traces of more complex substances. These strands can stretch for light years, like faint, wandering threads in the larger fabric. They are places where the nebula has not yet been fully stripped and heated, where the raw material for future stars still lingers in a quieter, more sheltered state. Farther out from the bright central cavity, the Orion Nebula is wrapped in a more extensive cloud of cooler, denser gas. Here, bright stars and glowing hydrogen intermingle with dark lanes of dust that wind and twist, forming shapes that sometimes look almost familiar: pillars, waves, silhouettes that the human mind wants to turn into animals or faces. Behind these curtains of dust lie hundreds of objects that ordinary visible light cannot reveal. Protostars still deeply buried, disks not yet eroded, and small clumps of gas just beginning to gather. Infrared observations, however, can reach into these hidden layers. By combining data from telescopes that observe different wavelengths, astronomers have counted hundreds of protostars in this wider region of Orion, each one at its own stage along the path from cloud to star. Their numbers are highest in the more strongly compressed central parts of the nebula and sparser farther out, where gravity has not pinched the gas quite as tightly. Almost all of them are very young, still drawing in material and not yet settled into the quiet, steady burning that will someday define their adult lives. The basic story guiding this understanding is, in its outline, simple and graceful. A large cloud of interstellar gas, perhaps nudged by an external shock or by its own internal instabilities, begins to fragment. Gravity, always pulling inward, starts to win over the random motions of the gas in certain regions. Those regions grow denser, and as they do, they attract still more material. In time, the cloud that was once nearly uniform breaks into a collection of knots, each one destined to become a star or a small system of stars. Astronomers call such places stellar nurseries or regions of star formation. At first, the collapse of each knot is quite rapid. As material falls inward, the center grows hotter and denser. Eventually, though, a temporary balance sets in. The heat generated by compression increases the internal pressure of the gas, pushing outward and partly halting the collapse. The young object, a protostar, reaches a kind of pause, not yet a true star, but no longer just a featureless clump in the cloud. Around it, the remaining material does not fall straight in. Because of even a small amount of rotation, it spreads into a flattened, swirling disk. Inside this disk, countless collisions and gentle stickings begin to happen. Dust grains bump together and cling, forming larger particles. These collide again, slowly building pebbles, rocks, and, over immense time, the solid cores of planets. Meanwhile, other parts of the disk feed the growing protostar, streaming along spiral arms of gas toward the center. The system is dynamic, messy, and beautiful, a balance of falling in and being blown out. The young star's magnetic field, tangled up with the disk, adds another layer to the story. Ionized gas in the disk can be guided along invisible magnetic lines, funneled toward the star's poles, and then flung outward in narrow jets at high speed. These outflows can reach velocities of hundreds of kilometers per second. When they slam into the surrounding gas, they create small, bright shock regions that astronomers call Herbig-Haro objects, glowing knots and arcs where kinetic energy is transformed into light and heat. In images, Herbig-Haro objects can look like tiny comets, bow shocks, or overlapping bubbles, often tinged in greens, reds, and blues depending on which atoms are being excited. They do not last long on cosmic timescales. Over tens of thousands of years, they change shape, fade, and disperse as the jets weaken and the surrounding gas is swept aside. In that time, they may travel a light year or two away from their source, like sparks drifting from a fire. In busy star-forming regions such as Orion, where many newborn stars are launching jets at once, the result is an intricate, overlapping pattern of these structures, each one marking a moment in the life of a young star's outflow. Astronomers have cataloged a few hundred Herbig-Haro objects so far, and they suspect that our galaxy contains many more, scattered wherever stars are forming in dense groups. Seen together, they hint at how energetic the earliest stages of stellar life can be, even while the stars themselves are still wrapped in cocoons of dust. In Orion, there is another related and striking phenomenon: fast-moving clumps of gas that observers sometimes call bullets. These are compact knots, hundreds of times larger than the Earth-Sun distance, racing through the nebula at remarkable speeds. As they plow into thinner hydrogen clouds, they drive shock waves ahead of them, carving out elongated cavities and lighting up the gas they encounter. Spectral studies show that their leading edges contain atoms of elements such as iron, glowing strongly in infrared light. These bullets seem to be only about 1,000 years old, a brief heartbeat in the life of the nebula. Their exact origin remains uncertain. They may have been launched by a violent interaction between massive young stars, or by some sudden, energetic event deep in a cluster. Whatever their source, they remind us that even in the quiet-looking beauty of a nebula, there can be episodes of great violence, sending ripples and fragments outward into the surrounding medium. When you zoom out even further, the Orion Nebula reveals itself as just one luminous knot in a much larger structure called the Orion Cloud, or the Orion Molecular Cloud Complex. This sprawling arrangement of gas, dust, and young stars stretches across hundreds of light years and covers much of the sky region we know as the constellation of Orion. Within this broader complex, other well-known nebulae reside, each with its own character. One of the most famous is the Horsehead Nebula, a dense pillar of dust whose shape, in silhouette, resembles the head of a horse rising from a sea of light. It is only a few light years across, yet its outline has become iconic in images of the night sky. The Horsehead stands out because it is set against a bright, red-tinged background of glowing hydrogen gas. The contrast between the dark, cold dust and the warm emission behind it makes the structure sharp and unforgettable. Another great feature of the Orion region is Barnard's Loop, a vast, faint arc of emission that sweeps across a large patch of sky. This enormous, curved nebula spans a few hundred light years and is thought to be the residue of several supernova explosions that occurred a few million years ago. Those ancient blasts sent shock waves outward, compressing the surrounding gas into a shell. Over time, that shell has cooled and recombined, and the light of young stars embedded within it now causes it to glow softly in reddish tones. When you see the larger Orion complex in composite images, Barnard's Loop looks like a gentle, ghostly ring encircling the main star-forming regions. Against this grand backdrop, the bright patch we call the Orion Nebula is almost a fragile detail. By the standards of the universe, it is a temporary structure. The same forces that make it shine intense radiation, powerful stellar winds, energetic jets, and turbulent gas motions are also steadily tearing it apart. The hot central cavity grows as gas is pushed outward. Dust grains are destroyed or carried away. The denser filaments that once fed star formation are eaten into, thinned, and eventually dispersed. Astronomers estimate that Orion's bright cloud has already lost a large fraction of its original mass. Much of the gas that once filled this region has been blown into space or locked up into stars and planets. In perhaps 100,000 years or so, a blink in cosmic history, the nebula will fade. The luminous fog will thin and vanish, leaving behind an open cluster of young stars shining in relative clarity. Such a cluster would be somewhat like the Pleiades, the small, tight group of blue-white stars visible in the constellation Taurus. For a while, the young suns born in Orion will travel together, crossing the galaxy as a loose family, bound by their shared origin and their mutual gravity. But even that state is not permanent. Over tens and hundreds of millions of years, the cluster will gradually dissolve. The stars will drift apart under the influence of the galaxy's larger gravitational field and encounters with other masses. One by one, they will be scattered along separate paths, joining the wider population of stars in the Milky Way. Lying where you are now, with the roof or sky above you, it is hard to feel that kind of motion and change. The constellation of Orion returns each year with its familiar pattern, and the nebula in his sword appears, to the eye, the same. Yet behind that apparent steadiness, whole regions are forming, glowing, colliding, and dispersing. Protoplanetary disks are swirling toward planets. Jets are cutting paths through gas. Shells from ancient explosions are expanding and fading. To notice this, even in imagination, is to sense that the universe is not a frozen picture, but a gentle, ongoing story, and that somewhere in that story, our own star and its planets have also had their time of being cradled in a cloud, lit for the first time, and set adrift into the dark. When you follow a star from its cradle in a nebula, all the way to its last quiet glow or final violent outburst, one simple rule keeps appearing beneath all the details. What happens to a star is, more than anything else, decided by how heavy it is. Mass is the quiet number that sets the tempo of its entire life. For stars on the lighter side, those with less than about 8 times the mass of our Sun, the story is long and relatively gentle. They spend billions of years in their main phase, quietly fusing hydrogen into helium in their cores. Eventually, that fuel runs low. The core contracts, the outer layers swell, and the star becomes a red giant. It sheds some of its outer gas in soft, glowing shells, and at the center, the hot, dense core is left behind as a white dwarf, a small, Earth-sized ember made of tightly packed matter. A white dwarf no longer burns fuel in its heart. It shines for a time with the leftover heat stored inside it, cooling ever so slowly. Over unimaginably long spans, far beyond the current age of the universe, it is expected that such objects will grow dimmer and dimmer, until they become what astronomers call black dwarfs, cold, dark remnants that no longer give off their own light. That final stage is still a theoretical whisper, because the cosmos is not yet old enough for any white dwarf to have cooled that far. But in principle, this quiet path from main sequence to red giant to white dwarf and then eventually to black dwarf is the fate awaiting more than 99% of all stars, including our own Sunday. Heavier stars carry a different destiny. When a star begins its life with more than about 8 solar masses, its core becomes hot and dense enough to fuse not just hydrogen into helium, but heavier and heavier elements in quick succession. The star burns its nuclear fuel much more rapidly, living fast and bright. Near the end, its core becomes layered like an onion, with different elements fusing in shells. This uneasy structure cannot last. When the core can no longer support itself, it collapses suddenly, and the outer layers are hurled away in a supernova explosion. For a brief time, that explosion can outshine an entire galaxy, casting out shockwaves and newly forged elements into space, enriching future generations of stars and planets. What remains in the center after such a cataclysm is the former core of the star, squeezed into an object of staggering density. The fate of this remnant, too, is written by mass. If it is heavy enough, the core's own gravity overwhelms every known form of pressure, and it collapses further into a black hole, a region where the pull of gravity is so intense that not even light can escape. But there is another outcome, perched in a narrow range between too light and too heavy. If the mass of the stellar remnant lies in a band of roughly 1.5 to a bit more than 2 times the mass of the Sun, the collapse is halted at an intermediate, astonishing state. The result is a neutron star. Inside a neutron star, matter is pushed to extremes that are hard to picture. The gravitational forces are so strong that they crush atoms themselves. Electrons are squeezed into protons, and together they fuse into neutrons. The ordinary picture of atoms' nuclei with orbiting electrons stops being useful. What you are left with is a ball of superdense, neutron-rich matter, with properties that are still the subject of intense study and curiosity. Neutron stars are rare by the standards of the galaxy. For every 1,000 or so ordinary stars, calculations suggest there may be only one neutron star. They are also tiny compared with regular stars, perhaps only a couple of dozen kilometers across, about the size of a city. That small size, combined with their lack of ordinary visible light, makes them extremely difficult to spot. For a long time, they were ghosts in our theories, predicted on paper, but invisible to our instruments. It was only with the development of radio and X-ray telescopes that these objects began to reveal themselves. The first strong observational evidence for a neutron star came in 1967, when astronomers detected a signal that puzzled them deeply. A series of radio pulses arriving with an almost unbelievably regular rhythm. At first, there was speculation about artificial sources, so precise was the ticking. But further study showed that this was nature's clockwork, not anyone's transmitter. The signal came from a rapidly spinning neutron star whose beams of radiation were sweeping across Earth like the light from a lighthouse. This kind of neutron star is called a pulsar. Its powerful magnetic field and rapid rotation work together to generate narrow beams of radiation that stream out from near its magnetic poles. If one of those beams happens to intersect our line of sight, we see a pulse each time the star spins, sometimes many times per second. The conservation of angular momentum, the same principle that makes a spinning ice skater turn faster when they pull in their arms, means that when a massive star's core collapses into a much smaller neutron star, its rotation speeds up dramatically. A slow-turning giant becomes a compact object spinning with extraordinary swiftness. Today, thousands of neutron stars are known, the majority of them detected as pulsars. Their pulses can be observed across vast distances, even many thousands of light-years away, especially in radio and X-ray light. Astronomers have cataloged over 3,000 such objects, and most of them appear to live solitary lives, moving alone through space. About 90% are single stars, without nearby companions. The remaining fraction belong to binary or multiple systems paired with other stars. Often, the partner in such a system is a red giant or an ordinary main sequence star. In some rare cases, however, two neutron stars end up locked in orbit around one another. This can happen when a pair of massive stars form together, live their luminous lives side by side, and then, also side by side, each reaches the end of its life. The first to explode becomes a neutron star, and the second follows later. The gravitational energy lost as the system rearranges itself brings the two remnants closer together, tightening their orbit and increasing their speed. One of the most intriguing examples of such a double system is a pair of pulsars known as PSRJ 737 3039. It lies around a few thousand light-years from Earth and is unique in that both members are active pulsars, each sending out its own beams of radiation. They whirl around one another in a tight dance, offering astronomers a rare chance to study how two neutron stars interact in strong gravity. The more massive of the pair weighs in at about a third more than the Sunday. Despite that, its entire mass is compressed into a sphere only on the order of tens of kilometers wide. It spins furiously, completing dozens of rotations every second, flicking its beams past us again and again with a precision that rivals any mechanical clock. Its companion is a little lighter, with a mass only slightly greater than the Sun, and it rotates more slowly, turning once every few seconds. Together, they orbit each other on a tight path, their mutual gravity tugging and twisting space-time around them. If you could somehow hover nearby, at a safe distance, you would see nothing like a familiar star. Instead of a large glowing disk, each neutron star would be a tiny, blinding point, surrounded perhaps by faint arcs where its beams interact with surrounding material. Everything about the system would be extreme: the speeds, the densities, the gravity. Yet the stars themselves, though so compact, are made of matter, not entirely unlike the atoms in your own body, just pressed into a radically different state. To understand how incredible that compression is, it helps to imagine peeling back the layers of a neutron star in your mind. Using theories of their internal structure and the results of complex computer models, astronomers have built a tentative picture of what lies beneath their surfaces. The outermost layer, in this picture, is sometimes called an atmosphere. But the word does not mean what it does for Earth or Venus. Around a neutron star, this atmosphere is incredibly thin and shallow. Instead of extending for dozens or hundreds of kilometers, it may be only a few millimeters thick for older, cooler neutron stars. For the youngest and hottest of these objects, fresh from a supernova, the atmospheric layer can reach a few centimeters in depth. It is made of highly ionized plasma, the stripped remains of the star's outer material. Hydrogen and helium, the most common elements in stars, likely dominate this skin, though heavier elements can also be present, depending on the star's history. But the exact composition is still an open question in many cases, because the conditions are so extreme and difficult to reproduce. Temperatures here can be millions of degrees, and the surface gravity is mind-bendingly strong. So strong that a tiny vertical distance matters. Beneath this scorching film lies what is called the outer crust, This layer can be a few hundred meters thick, which sounds like a lot until you remember that it contains much of the mass of a city-sized object. Here, gravity is strong enough to squash the familiar structure of matter. Atoms are packed together into a dense lattice, and while the electrostatic forces that keep protons and electrons in their places have not yet fully given way, they are under intense pressure. Inside the crust, the particles that make up matter are pulled in multiple directions at once. Gravity drags everything inward. The neutron star's powerful magnetic fields thread through the region, influencing the motion of charged particles. Electrostatic forces try to keep like charges apart and unlike charges together. The star's rapid rotation adds centrifugal effects, especially near the equator. All of these influences combine to place the crust under continual stress. Sometimes, that stress builds up until the crust yields. When it does, a kind of starquake can occur, a sudden rearrangement of the rigid outer layer. These events can cause tiny changes in the neutron star's rotation rate, and in some cases, they may release bursts of high-energy radiation. The deformations themselves are small in absolute height, perhaps a ridge a millimeter high, or a crack a centimeter across. Yet in the context of the neutron star's gravity, such structures are enormous. A bump that size can contain more mass and stored energy than an entire mountain on a planet like Mars or Earth. If you could keep descending in your mind's eye, pushing deeper toward the center, you would find that the crust does not have a sharp, simple boundary. It merges gradually into inner layers where the pressure grows even more crushing. As you go down, electrons are increasingly forced into atomic nuclei, combining with protons and creating more neutrons. The familiar distinction between separate atoms begins to blur. Matter transitions through exotic phases that do not exist elsewhere, at least not in any place we can visit. The exact details of these phases, whether the inner core of a neutron star is made of superfluid neutrons, or includes free quarks, or forms other strange states, are topics of active research. But even without knowing every detail, the broad outline is clear enough to inspire awe. What started as a giant ball of burning gas ends, in some cases, as a tiny, massively heavy sphere where the basic building blocks of matter are pressed into new arrangements. From where you lie listening, this all may feel distant, like a story from another world. Yet the atoms that make you were forged in stars that lived and died long ago, sometimes quietly, sometimes in the violence of supernovae. The same laws that shape their lives, the pull of gravity, the pressures of heat and density, the quiet rule of mass, also shape the space and time you move through. To imagine a neutron star, or a white dwarf, or a black hole, is to imagine one possible future for starlight. And in the soft hours of night, letting your thoughts drift there can be strangely calming, a reminder that change, even at its most extreme, is part of a larger, continuous unfolding, and that somewhere in that unfolding, you and your small, warm corner of the universe are gently included. Deep inside those collapsed stars, where gravity has already squeezed matter beyond anything we know on Earth, the story continues in silence. As the pressure rises and atoms are pushed closer and closer together, electrons are forced into protons. The two merge, and in that brief, intense act, a neutron is formed along with another, much more elusive passenger, a neutrino. Neutrinos are almost like whispers of the process. They carry away excess energy and slip through matter as if it were not there at all. Even inside a neutron star, most of them barely notice the dense material around them. They stream outward and escape into space, taking with them a record of the furious changes that happened in the star's heart, while the neutrons remain behind, packed ever more tightly. Beneath the inner layers of the crust, where the last hints of ordinary atomic structure fade, lies what astronomers call the outer core. Here, the matter is made almost entirely of neutrons, crowded together in a way that defies easy analogy. The density is believed to be many times higher than that of the nucleus of an atom. If you tried, in imagination, to compress the whole Earth to this same degree, our planet would shrink until its radius was only a fraction of a kilometer. A mere teaspoon of such material would weigh billions of tons. In many neutron stars, this neutron-rich outer core may extend all the way to the center, filling the object from just beneath the crust down to its very heart. In more massive examples, there might be something even stranger, deeper inside, an inner core of matter in an even more exotic state. What exactly that state is remains one of the open questions of modern astrophysics. One idea suggests that at the very highest pressures, even neutrons themselves could be broken apart. Their constituent quarks, the more fundamental particles inside them, might roam more freely, forming what is sometimes called quark matter. A star, made largely of such stuff, would be a quark star. Other hypotheses imagine cores where new kinds of particles appear, hyperons, or condensates of unfamiliar mesons, creating forms of matter with unusual and subtle properties. For now, all of these possibilities live mostly in equations and models. We do not yet have direct observations fine enough to say exactly what lies at the centers of these dense remnants. Stepping back from their internal mysteries and looking again at a system like PSR J737, 3039 as a whole, several remarkable features emerge. The two pulsars in this pair do not drift lazily around one another. Calculations show that they orbit their common center of mass on a tight, slightly stretched path, packed into a remarkably small volume of space. On average, the distance between them is less than the diameter of our Sunday. Because they are so close, their mutual orbital speed is extremely high, reaching hundreds of kilometers per second. They complete an entire dance around each other in just a couple of hours. From our calm perspective, where planets take months or years to circle their stars, this is dizzyingly fast. Such rapid motion in such a strong gravitational field naturally brings in the subtle effects described by the theory of relativity, effects that would never show up in an ordinary classroom diagram of orbits. One of these effects appears in the timing of the pulsar's own rotations. Careful observations show that when the two neutron stars come closest to each other in their orbit, the rate at which each pulsar spins, as seen from Earth, changes ever so slightly. The period between pulses stretches by a tiny amount, just a few tens of millionths of a second, and then returns to its previous value as they move apart again. That change is minuscule, but the regularity of pulsar signals makes it measurable. Classical physics, the kind you use to calculate the motion of a ball or a planet under Newton's law of gravity, has no easy way to account for this behavior. Relativity, however, anticipated something like it long ago. In Einstein's picture, time itself passes at different rates depending on the strength of the gravitational field and the speed of motion. Nearer to a massive object, or at higher speeds, time dilates, stretching out. In the moment when the two pulsars are at their closest approach, these relativistic effects are strongest, and the pulses we receive reflect this slight slowing down. Another subtle effect shows up when one pulsar passes behind the other from our point of view. During these mutual eclipses, the signal from the more distant star must travel through the curved, intense gravitational field of its companion. As the radiation climbs out of that gravitational well, it loses a small amount of energy. Lower energy light has a longer wavelength, so the signal is shifted toward the red end of the spectrum. This gravitational redshift is another direct sign that space and time around the neutron stars are being significantly warped by their mass. Their orbit itself carries further evidence. In classical mechanics, two objects in an elliptical orbit would trace the same path over and over, like a perfectly drawn loop. In reality, the point of closest approach, the periastron slowly rotates around so that the ellipse turns in space over time. This gradual twist of the orbit, called relativistic precession, was first noticed in our own solar system in the orbit of Mercury, whose path shifts by a tiny angle over a century. Around the double pulsar, the effect is immensely stronger. The point of closest approach sweeps forward by many degrees each year, marking this system as one of the most extreme known laboratories for testing general relativity. If you let your mind rest for a moment on the idea of planets in such an environment, the picture becomes even more eerie. Any worlds that might once have circled the progenitor stars would have had to survive not one, but two supernova explosions, each one blasting out intense radiation and throwing off large amounts of mass. More likely, any planets that exist now would have formed later from whatever material remained bound to the system. In either case, they would be bathed in high-energy radiation and subject to strong tidal forces. Our usual methods for finding exoplanets, watching for tiny dips in a star's light as a planet passes in front, or measuring small wobbles in the star's motion, are poorly suited to a system like this. Pulsar timing, a very precise technique, can reveal planets around some neutron stars. But in the case of this particular pair, no clear planets have been confirmed. Even if small worlds do exist there, their surfaces would be far from welcoming. The environment would be freezing in temperature, yet drenched in harmful radiation, a combination that makes them seem like settings for abstract thought, more than places any life could easily call home. Still, the system speaks to us in another, more subtle way. As the pulsars whirl around each other, they constantly stir the fabric of space-time itself, sending out ripples called gravitational waves. These waves carry energy away from the system. As that energy is lost, the orbit shrinks, and the two neutron stars spiral slowly closer together. The change in their separation is tiny on human scales, only a handful of millimeters per day, but over millions of years, it adds up. By tracking the pulsar's timing with exquisite care, astronomers can measure this gradual in-spiral and confirm the predictions of general relativity with high precision. Extrapolating into the future, they estimate that in tens of millions of years, the two stars will finally merge. In that final moment, their combined mass may collapse into a black hole. The merger will unleash a flood of gravitational waves, racing outward at the speed of light, and a burst of electromagnetic radiation that could, for a brief time, outshine many of the stars in the sky. By the time that event happens, countless other changes will have taken place in our galaxy. New stars will have formed, old ones will have faded. Whether anyone will be here to see that distant flash is an open question, but the waves from such mergers do not care. They pass silently through everything, bending distances by amounts too small for our bodies to notice, yet just large enough for sensitive instruments to record. From that intense and compact system, the story can drift back outward toward quieter neighborhoods. Compared with the crowded regions near the galactic center or the bustling star-forming clouds like Orion, The outer area around our Sun is relatively sparse. By galactic standards, the space within a few dozen light-years of the solar system is thinly populated. Still, within a sphere about 15 light-years in radius, astronomers have found on the order of 50 separate stellar systems. Some host only a single star. Others contain 2, 3, or more, bound together by gravity. Altogether, the total number of individual stars in this volume reaches into the 60s. Many of these nearby stars are accompanied by planets or by leftover disks of gas and dust where planet formation may still be ongoing. They make up our local stellar environment, the Sun's quiet neighbors, scattered through the dark. To get a sense of them, you can imagine slowly pulling away from the solar system, letting the familiar warmth of our own star recede into a small, bright point, and gliding outward through the invisible medium between systems. After traveling a handful of light years in this thought journey, you would come upon one of our closest neighbors, a dim little star known as Barnard's Star, or GJ 699. It lies at a distance of roughly 6 light-years from the Sun, a small red dwarf moving briskly through space. Though it is so faint that you cannot see it with the naked eye, Barnard's Star has a kind of quiet notoriety among astronomers because of how quickly it appears to drift across the sky when measured against more distant background stars. This apparent motion, called proper motion, is a combination of the star's true motion through space and our own movement around the Sunday. In the case of Barnard's Star, the effect is particularly strong. Over the course of less than 2 centuries, it would seem to shift by an angle roughly equal to the diameter of the Moon, as seen from Earth. That might not sound like much, but compared with most stars, which creep only slowly across the sky on human timescales, it is remarkably swift. Part of this is due to the star's nearness. Part is due to its substantial speed relative to the Sunday. Barnard's Star is moving toward our solar system at over 100 kilometers each second. In about 10,000 years, a long time for us, but a short step in astronomical terms, it will come even closer, becoming our nearest stellar neighbor at a distance of just under 4 light-years. Even then, though, it will remain a very faint presence, visible only through telescopes. Its intrinsic brightness is simply too low to make it stand out in the night. Barnard's Star is a lightweight compared with the Sunday. Its mass is only a small fraction of our stars, and its radius is correspondingly smaller. Like other red dwarfs, it is relatively cool, with a surface temperature far below that of the Sunday. Because a star's brightness depends strongly on both its size and its temperature, this means Barnard's Star shines with only a tiny fraction of the Sun's luminosity. From a distance, it would resemble a ruddy ember rather than a blazing furnace. Yet, in another sense, stars like this are the quiet workhorses of the galaxy. They burn their fuel so slowly that they can live for tens or hundreds of billions of years, far longer than stars like the Sunday. If you could sit on a planet that somehow orbited close enough to Barnard's Star to receive a comfortable amount of light and warmth, your sky would be dimmer, your days redder, but your star's lifespan would stretch far beyond the timescales we usually think about. Here, in the soft dark of your own night, the details of those distant systems can feel abstract. Pulses and quakes in collapsed stars, red dwarfs gliding by over millennia. But they are all part of the same quiet pattern. Heavy stars live fast and leave behind dense, exotic remnants. Lighter stars glow more gently and for longer. Neighbors drift in and out of our vicinity over ages, sometimes unnoticed. While you breathe and listen, All of that is unfolding in the background, not demanding your attention, but still there, steady as a heartbeat far away. When astronomers watched Barnard's star inch its way across the sky for decade after decade, they were not just tracking a wandering point of light. Tiny irregularities in its motion hinted that something invisible might be tugging on it. In 2018, after about 20 years of patient measurements, an intriguing pattern emerged. The star's path seemed to wobble in a way best explained by the pull of a planet, a world circling in the cold, dim light of this ancient red dwarf. From the data, a picture slowly took shape. The candidate planet appears to be more massive than Earth, at least a few times heavier, making it a so-called super-Earth. It circles its star on a wide, cold path, taking roughly 230 days to complete one orbit. Astronomers call it Barnard's Star B, or GJ 699b. It does not pass directly between its star and our line of sight, so it does not produce the little dips in starlight that have revealed so many other exoplanets. Instead, it reveals itself indirectly through the way its gravity gently tugs on its parent star. Because Barnard's star is so faint, the planet receives far less warmth than Earth does. The light that reaches it is weak, more like the glow of a distant ember than the fierce blaze you know from the daytime sky. Calculations suggest that the amount of energy falling on this world is tens of times lower than the sunlight that reaches our planet. Under such meager illumination, the surface temperature would be far below freezing, perhaps around 100 degrees above absolute zero, a place of deep, persistent cold where any exposed water would be locked in ice. On the surface, it would seem a harsh and frozen world. But not all warmth comes from above. Inside planets, other sources of energy can be at work. The slow decay of radioactive elements in the rock, the gentle kneading of tides if the orbit is not perfectly circular. On Earth, these internal heat sources are overshadowed by sunlight at the surface, yet they still drive volcanic activity and the movement of plates. On a planet far from its star's warmth, internal heat could be the main source of energy. If Barnard's Star B has a thick shell of ice and rock, it is conceivable that beneath that shell, there could be a layer where the temperature rises just enough for water to remain liquid. A hidden ocean, insulated from the vacuum of space by a crust of ice, could persist for billions of years, fed not by starlight, but by heat from below. In such a place, if the right chemistry is present, simple forms of life would have had an extraordinarily long time to emerge and slowly adapt. The timescales here are generous. Barnard's star is thought to be one of the oldest stars in our neighborhood, perhaps more than 10 billion years old, older than the Sun, older than the Earth, older than any mountain or ocean you know. Compared with the full lifetime of such a red dwarf, even 10 billion years is only a portion of its story. If any slow, patient biology is unfolding in the hidden depths of a planet there, it has had aeons to take its time. Because of its proximity and its motion, Barnard's star has long occupied a special place in plans for future journeys beyond the solar system. In some distant chapter of human exploration, if ships ever do slip free of the sun's immediate embrace and head for the nearest stars, this small red beacon may well be one of the first destinations. For now, it keeps its secrets at a quiet distance, and the possible ocean under its ice, if it exists, remains an untested dream. If you let your imagination swing to the other side of the sun's neighborhood, you encounter almost the opposite kind of star. Not faint and red, but dazzling and white. Sirius, often called the dog star, is the brightest star in the night sky. On a clear evening, it sparkles with a hard, blue-white light that seems to shimmer as it shines through Earth's turbulent air. It lies about 8.5 light-years away, not the closest star to us, but the most visually striking. To the naked eye, Sirius looks like a single brilliant point, yet careful observations have revealed that it is actually a pair of stars bound together by gravity. The main component, Sirius A, is a hot, luminous star about twice the mass of the Sun and somewhat larger in size. Its surface is so hot that it glows with a bluish-white color, and it pours out many times more light than our own star does. If you could somehow swap the Sun for Sirius A in our sky, daylight would become almost blindingly bright. The second member of the system, Sirius B, is a very different creature. It is a white dwarf. The compact core left behind after a once larger star exhausted its nuclear fuel and cast off its outer layers. Though its mass is close to that of the Sun, its radius is only a fraction of Earth's. Picture something with the weight of a star curled into a ball about the size of a planet. Its surface temperature is extremely high, tens of thousands of degrees, so it shines fiercely per square centimeter. But because it is so small, its total luminosity is tiny compared with Sirius A. Against the glare of its brilliant companion, Sirius B is almost lost, detectable only through careful measurements. These two stars travel around their common center of mass on elongated paths, completing one orbit roughly every half-century. At present, they are separated by a distance comparable to the span of the outer planets in our solar system. Long before Sirius B became the faint white dwarf we see today, it would have lived a brighter, faster life, swelling into a red giant and shedding its outer layers. That transformation, perhaps 100 million years ago, likely disturbed any early disk of gas and dust that might have been forming planets around the pair. This history may help explain why no planets have yet been confirmed in the Sirius system, despite sustained searching. It could be that planets were once there and were stripped away or destroyed when the more massive star swelled and cast off its shroud. It could also be that planets never formed in stable orbits to begin with, their birth disrupted by the energetic youth of the two stars. Another possibility is more mundane. If planets are present, but their orbits are tilted just so, our usual methods for detecting them, especially watching for regular dips in starlight as they transit, may simply not catch them. From our vantage point on Earth, the long, slow ballet of Sirius A and B plays out too gradually to be noticed in a single lifetime. Over tens of thousands of years, however, the whole system is moving relative to us. Calculations show that Sirius is slowly drawing nearer and will reach its closest approach in about 60,000 years, brightening modestly as our separation shrinks to around 7.5 light-years. After that, it will slowly recede, its intense sparkle softening ever so slightly as it glides away. Far in the future, on timescales that make even ancient Barnard's star seem young by comparison, Sirius A will exhaust the hydrogen in its core. It will expand into a red giant, casting a warm, swollen glow over any nearby worlds, if they exist, then shedding its outer layers into space. For a short time, its brightness will surge, perhaps thousands of times its current luminosity. Then, like its companion, it will contract into a white dwarf. The pair will live on as two small, dense embers, slowly cooling together over hundreds of billions of years, their brief era as the brightest star in our sky, long past. From that intense and shimmering region, Imagine drifting outward once more, looping gently back past the sun, and then curving away toward another, quieter star. About 14 light-years from Earth, there is a small red dwarf called Wolf 1061. It is much less massive than the Sun, only a fraction of its weight, and its radius is smaller as well. Its surface is relatively cool by stellar standards, glowing with a steady, deep red light. To the unaided eye, it is invisible. Only telescopes reveal its presence. What makes Wolf 1061 especially interesting is not the star itself, but the company it keeps. This dim ember appears to be orbited by at least 3 rocky planets, all roughly similar in composition to Earth. In this compact system, worlds hug close to their small star, circling in periods of days or weeks rather than months or years. Because the star is faint, the region where temperatures might be moderate enough for liquid water lies much nearer in than it does around the Sunday. The innermost of these planets, known as Wolf 1061b, skims close to its star on a tight orbit, completing a circuit in only about 5 days. It is somewhat larger and more massive than Earth, a super-Earth, but its proximity to the star subjects it to intense radiation and tidal forces. It is likely tidally locked, always showing the same face to the star, just as the Moon always shows the same face to Earth. On its day side, the surface would be baked under constant, unsetting light. On its night side, darkness would be endless and cold. Flares and stellar winds from the active red dwarf would lash the planet's day side relentlessly, making it difficult for an atmosphere to survive. Any gases might be stripped away over time, leaving bare rock exposed to space. As a home for life, at least life as we understand it, such a world seems deeply unfriendly. It is a place to imagine only briefly before letting your thoughts move outward to cooler orbits. The second planet, Wolf 1061c, lies somewhat farther from the star, circling in about 18 days. This does not sound like a long year, but around such a faint sun, this orbit places the planet in what is often called the habitable zone, the region where, with the right kind of atmosphere, temperatures at the surface might allow liquid water to exist. Wolf 1061c is more massive than Earth, perhaps 3 to 4 times heavier, and its radius is estimated to be around 1.5 times that of our planet. On its surface, gravity would be stronger, pulling you down with more insistence, making your steps feel heavy and your movements slower. Despite sitting in the habitable zone, the planet receives less energy from its star than Earth does from the Sunday. Its equilibrium temperature, the temperature it would have without an atmosphere to trap heat, is well below freezing, perhaps similar to or somewhat warmer than conditions on Mars. But atmospheres can do a great deal. A dense blanket of gases rich in greenhouse molecules could hold on to heat, smoothing out temperature differences between day and night, between equator and pole. Under such a sky, liquid water might flow or pool in places, and clouds could drift, reflecting light and reshaping the climate. If that is the case, Wolf 1061c becomes one of the intriguing nearby candidates in the ongoing search for potentially habitable worlds. It is not a twin of Earth. Its gravity, its sky, its day length, and its seasons would all be different. Yet in the soft realm of possibility, one can imagine standing under a dimmer, redder sun, feeling a stronger pull underfoot, looking up at a sky perhaps streaked with long, high clouds, tinted with a faint crimson glow. The third known planet in the system, Wolf 1061d follows a more stretched out path. Its orbit is more elongated than those of its inner siblings, carrying it from relatively close to the star to much farther away over the course of its year. That year, in this case, lasts on the order of many months. As it journeys along this eccentric route, the amount of starlight it receives changes significantly. When it is nearer to the star, its surface and any atmosphere would warm. When it is farther away, they would cool. Such an orbit could make the climate of Wolf 1061d, if it has a solid surface and atmosphere, more variable and challenging. It may spend long stretches in deep cold, with only brief passages through milder conditions, or, depending on the thickness and composition of any atmosphere, the planet's climate may be able to buffer those changes, storing heat and releasing it slowly. For now, all of this remains conjecture. What we do know is that this small red dwarf, invisible to the naked eye, is surrounded by a surprisingly rich set of rocky worlds. Stepping back from the details of each system, you can picture the Sun's broader neighborhood as a gently scattered cluster of tiny fires in a dark room. Some, like Barnard's Star and Wolf 1061, are faint red embers, barely noticeable without help, yet ancient and long-lived, attended by planets that circle close in tight, fast years. Others, like Sirius, burn hot and bright, lighting up our sky from far away, their own histories, shaped by the rise and fall of massive stars and the compact remnants left behind. All of these stars, with their planets and possible oceans, their frozen surfaces and tempestuous skies, share the same galaxy with you. While you lie still, breathing quietly in your own small patch of night, they move along their slow trajectories. Worlds freeze and thaw, atmospheres thicken and thin, stars brighten and fade. The distances are immense, the timescales vast, but they are part of the same universe that holds your heartbeat and your thoughts. Letting that awareness settle around you like a soft blanket, you might feel, for a moment, less alone under the sky. Farther out in the Wolf 1061 system, the outer planet moves along its stretched, wandering path. Its mass is estimated to be several times greater than Earth's, heavy enough that it likely belongs to the family of super-Earths or small mini-Neptunes. If it is mostly rock and metal, its surface gravity would tug more firmly than the gravity you know, and its radius might be not much less than twice that of our planet. If instead it wears a thick, layered atmosphere around a smaller solid core, its apparent size could be larger still, its bulk wrapped in deep envelopes of gas. Because its orbit is quite elongated, this world spends part of its year closer to its star and part of it much farther away. Yet even at its nearest, it never enters the narrow band, where temperatures would comfortably allow liquid water beneath an Earth-like sky. Its path stays well outside the habitable zone, leaving it bathed in weak, reddish light. The surface, if there is one you could stand on, would likely be deeply cold and airless, or hidden under heavy, frozen clouds. For life as we understand it, this is not an inviting address, but it remains a valuable clue to how planets grow and migrate around small, long-lived stars. The wider space in which all of this unfolds is not empty. Wolf 1061 lies near the edge of what astronomers call the local interstellar cloud, a faint pooling of gas surrounding our solar system and some of its neighbors. This cloud is made mostly of hydrogen that is both thin and hot. Its temperature is thought to be around 7,000 degrees, yet the gas is so rarefied that, on average, only a fraction of an atom, occupies each cubic centimeter. Even compared with the already tenuous gas between the stars, this is especially delicate. For roughly the last 10,000 years, the Sun and its planets have been drifting through this region, carrying our small family of worlds through a very gentle fog. We are skimming near the edge of the cloud. Other nearby stars, like Alpha Centauri, already lie beyond it in a neighboring structure. Despite the high energies of the individual particles within the cloud, life on Earth is well shielded. The Sun's own wind of charged particles inflates a protective bubble, the heliosphere, around the planets, and any interstellar gas that makes it through that barrier is met by Earth's magnetic field and thick atmosphere long before it can touch the ground. Even so, traces of the wider environment do reach us. In Antarctic ice and in ocean sediments, scientists have found atoms of iron-60, a rare radioactive isotope not produced in large quantities on our planet today. Its presence hints at material that originated in stellar explosions and drifted through interstellar space before being swept up by the solar system, a faint dusting of the galaxy's history laid down grain by grain. Letting that background soften in your thoughts, you can picture our path bending gently toward another star, one at a very different moment in its life. AP Columbi is a faint red dwarf, less than 30 light-years away, and yet it is only about 40 million years old, a newborn by stellar standards. When this star was formed, the dinosaurs had been gone from Earth for tens of millions of years, and the world was slowly becoming more like the one you know. AP Columbi almost certainly did not form where we see it now. When astronomers trace its motion backward, it seems to point toward a distant open cluster called IC 2391, a loose group of young stars that share a common origin. At some point, the balance within that cluster was disturbed, perhaps when one of the more massive stars ended its life as a supernova. In the reshuffling that followed, AP Columbi appears to have received an extra kick, a small star flung outward from its nursery and sent gliding alone through space. Today, this little runaway is puzzling in ways that fit its age. It is light, only a small fraction of the Sun's mass, yet it shines several times more brightly than stars of the same type usually do, and its radius seems larger than theory predicts. The spectrum of its light also shows an unusually high abundance of lithium, an element that is quickly destroyed once a star's core settles into steady, main sequence burning. All of this tells us that AP Columbi is still contracting and adjusting, not yet fully settled into the long, quiet middle stretch of its life. Because it is so young, its surface is restless. Strong magnetic fields twist and reconnect, and from time to time, the star releases powerful flares and outbursts. During these events, its brightness can jump dramatically for a short while, and high-energy particles stream outward into the surrounding space. Any planets that might be huddled nearby would have their atmospheres stripped and battered. Observations suggest that within a few astronomical units there are no large companions yet, which is not surprising for a star so early in its story. For astronomers, AP Columbi is a natural laboratory for watching how small stars behave just after birth. From this young and temperamental ember, you can let your thoughts drift to a calmer neighbor, an orange dwarf known as Gliese 370, about 37 light-years away. It is smaller and cooler than the Sun, shining with a softer, golden light. Around it, at least one planet has been found, a world called Gliese 370b, discovered through the subtle wobble it imparts to its star. From that gentle tug, scientists infer that Gliese 370b is a rocky planet, a few times more massive than Earth, with a radius perhaps a third larger than our own worlds. On its surface, gravity would feel noticeably stronger. Each step would be a little heavier, each jump a little shorter. The planet orbits its star at a distance closer than Earth is to the Sun, taking only about 54 days to complete a year. Yet because its star is dimmer, the energy it receives is not overwhelming. If its surface reflects light, much as Earth's does, the average temperature might be pleasantly warm, only a little higher than the global average you are used to. The planet is far enough from its star that it is unlikely to be locked with one side in perpetual day and the other in endless night. Instead, it probably spins at its own pace, giving it a regular cycle of sunrise and sunset. That rotation would help spread heat around the globe, softening temperature contrasts between its bright and dark sides. With enough water and a suitable atmosphere, such a world could host broad, shallow seas, where light filters down through gentle waves and warms the upper layers of water. A somewhat higher gravity would tend, over long times, to smooth the terrain, making the tallest mountains rarer and encouraging wide basins where water could collect. In imagination, you might picture a planet of warm oceans and low, rounded continents, its coasts traced by long, quiet shorelines. For all these reasons, Gliese 370b was once counted among the more promising nearby candidates in the search for life beyond Earth. Later studies, however, suggested a more complicated picture. It may be that the planet's atmosphere is quite thick and rich in greenhouse gases, trapping heat more efficiently than Earth's. If so, surface temperatures could climb well above the first simple estimates, reaching values more reminiscent of Earth's deep past than its present. Even then, the range of possible temperatures leaves room for liquid water, especially in deeper oceans or in cooler regions toward the poles. During the Archean Eon, billions of years ago, Earth itself may have been wrapped in a heavy atmosphere and warmed by a stronger greenhouse effect than today. And yet, life managed not only to appear, but to persist in those conditions. Hot, mineral-rich waters and active geology provided niches where simple organisms could survive and slowly adapt. When astronomers look toward Gliese 370b, they sometimes think of that era not as a promise, but as a quiet possibility that somewhere under a different sky, chemistry has been given another chance to grow complex. The details of this distant world remain uncertain. No instrument can yet show us its clouds, its waves, or the color of its sky. What we have are careful measurements of starlight and motion, turned into numbers and then into stories by human patience and curiosity. Even so, it is enough to know that such a planet exists, circling a small, steady star not so very far away. As you lie here and let these places pass slowly through your mind, the cold outer planet of Wolf 1061, the thin gas of the local cloud, the young flaring AP Columbae, the warm, heavy seas that might roll on Gliese 370b, they begin to feel less like distant abstractions and more like quiet neighbors. Some are harsh, some are gentle, some are still in the throes of their beginning. Together they surround our own small world like scattered lights around a campfire, reminders that the galaxy is full of other skies, other nights, and other stories, unfolding whether or not anyone is awake to watch. If you pause for a moment and imagine looking back the way we came, our own sun would now be only one quiet spark among many. In this slow journey of the mind, we have drifted more than 50 light-years from the solar system. Within a sphere of space that wide, there are already well over 1,000 stars, some solitary and steady, some paired together, some woven into more intricate families. To the naked eye from Earth, most of these just look like single points of light. One of the most striking examples is a system in the constellation Gemini, a star that humans have watched since antiquity and named Castor. From the ground, it appears as a single bright point, the second brightest light in that constellation. Yet behind that one gleam lies a surprisingly complex arrangement. Castor is not one star, or even two, but six, three pairs of stars bound together in a layered dance. The two most luminous members, Castor A and Castor B, are hot, bluish-white stars, each brighter and more massive than the Sunday. Each of these, in turn, has a smaller red dwarf companion, circling close by like a faint ember near a lamp. The two bright pairs orbit their mutual center of mass on a broad path, separated by a distance comparable to the span of the outer planets in our own system. It takes centuries for them to complete a single revolution around one another. Farther out still, at several times that distance, there is a third pair, two dim red dwarfs so close together that they whirl around each other in less than a day, locked in a tight gravitational embrace. Together, all three binaries, the bright central pair and their two sets of smaller companions, are bound into a single family. From far away, their combined light blends into the one shining point we simply call Castor. So far, no planets have been firmly confirmed in this busy system. The light of the bright stars and the complexity of their orbits make subtle signals difficult to tease out. Still, hints have appeared. Small variations in timing and motion suggest that at least one of the red dwarfs may have a hidden companion, perhaps a brown dwarf, heavier than a planet, but not quite massive enough to ignite like a true star. And where red dwarfs are, especially in quieter outer corners of a system, rocky planets close in are not uncommon. If such a world circles one of Castor's dimmest members, the sky there would be an extraordinary sight. On one side, two nearby red suns might loom large, glowing like twin embers and tracing slow paths across the heavens. On the other side, twin bluish-white stars, farther away yet still dazzling, would pour down a cold, sharp light. Their combined brilliance would be hundreds of times greater than that of our moon. The planet's night might never be fully dark. Instead, it would sink into a gentle twilight, painted in shifting reds and whites. Whether such a place truly exists is something we cannot yet check. For now, it remains an illustration of how rich and varied skies can be around other stars. All of these systems, the quiet single stars, the pairs, the intricate families, sit together within a larger structure that our own sun also inhabits, a broader region of space, sometimes called the local bubble. This bubble is not a solid shell, but a vast, carved-out cavity in the gas of the Milky Way, stretching for a few hundred light-years. Millions of years ago, several massive stars in our region reached the ends of their lives. One after another, they exploded as supernovae, sending shock waves rushing outward. Those blasts swept up and heated the interstellar gas, creating a hot, thin interior surrounded by denser walls. Because the gas inside the local bubble is so hot, it wants to expand, and because it is so thin, its density is far lower than the average between stars elsewhere in the galaxy. The atoms here are mostly ionized. Their electrons have been stripped away by energy from old explosions and ongoing radiation. As they slowly recombine or are bumped to higher energy states again, they emit faint X-rays that drift through the bubble, a ghostly reminder of ancient violence, still echoing in the present. Our solar system sits within this bubble, moving along its own path, while the bubble itself interacts with neighboring regions. In the direction of the star Antares, for example, lies another cavity carved by supernovae, pressing gently against our own. Where their edges meet, gas has been compressed into ridges and filaments, places where future generations of stars may eventually form. Over tens of millions of years, as the Sun continues through the galaxy, our system will slide slowly across this landscape of cavities and walls. As you let that image float in your mind, our star drifting inside a vast, hot hollow, bordered by other hollows. The journeys we imagine from one nearby star to another become small motions within an even larger pattern. Huge bubbles carved by old explosions slowly shift and overlap as the galaxy turns. Far beyond the Sun's immediate neighbors, farther even than most of the stars we have been visiting, there lives a very different kind of object, glowing faintly through its own shroud of dust. Several hundred light years away lies a star, often referred to by its catalog name, and more familiarly as CW Leonis. It is a red giant in an advanced and delicate phase of its life, wrapped in thick layers of gas and carbon-rich dust that it has been shedding into space. If you could remove that veil and view the star's full extent, you would find a swollen, immense sphere. At the peak of its pulsations, its radius may reach hundreds of times that of the Sunday. Placed at the center of our solar system, its outer layers would engulf the orbits of Mercury, Venus, Earth, and Mars, and might brush the inner edge of the asteroid belt. Yet despite its size and glow, CW Leonis is not extraordinarily massive. Its mass is thought to be only a few times that of the Sunday. Its surface is relatively cool for a star, just a couple of thousand degrees above absolute zero, so it appears a deep, ruddy orange-red. But because its surface area is so vast, the total energy it emits is thousands of times greater than the Sun's. The light it sends out is heavily reddened and absorbed by the dust around it, making it appear dimmer and more mysterious from our vantage point. In infrared light, however, it blazes like a warm coal. CW Leonis was not always this way. In its youth, it would have been a smaller, hotter star, fusing hydrogen into helium in its core. Over billions of years, hydrogen in the center was gradually used up, leaving behind a core of helium ash. That core, no longer supported by energy from fusion, began to contract under its own weight, heating as it did so. Above it, a shell where hydrogen continued to fuse puffed up the outer layers, causing the star to swell. This slow expansion is the hallmark of a star entering its red giant phase. As the star grows, its outer layers become more tenuous and unstable, easier for radiation and stellar winds to push outward. Its color shifts toward the red as the surface cools. Deep inside, the contracting helium core continues to heat until, at a critical temperature and density, helium nuclei begin to collide and fuse into carbon and oxygen. This onset of helium fusion can be sudden and dramatic in stars of certain masses, a phase sometimes called a helium flash. In the star's interior, it is more like a rapid reorganization of the way energy is produced and transported than a literal flash. The core's temperature climbs steeply, and the internal structure adjusts. Over time, its brightness and pulsations can vary in complex ways as energy works its way outward through different layers. In CW Leonis, helium burning in the core and shells has created a rich supply of carbon. That carbon is carried outward by convective currents, slow loops of hot gas rising and cooler gas sinking, and some of it reaches the outer layers where temperatures are low enough for atoms to join into molecules and grains of dust. These carbon-based grains, mixed with other elements, form a thick, expanding envelope around the star. Starlight scattering off this material and being absorbed and re-emitted by it gives the region its characteristic glow. Because CW Leonis is not massive enough to ignite the next stages of nuclear fusion in its core, it will not go on to fuse carbon into heavier elements as the most massive stars do. Instead, over time, it will continue to lose mass, shedding its outer layers into space in a slow, uneven wind. Pulsations will make it brighten and dim, and arcs and clumps of ejected material will drift outward, forming intricate shells and filaments. Eventually, the star will expose its hot core, becoming a white dwarf surrounded by a fading shell of gas. From the right distance, that shell would appear as a planetary nebula, a delicate, glowing bubble slowly dissolving into the surrounding medium. The carbon and other elements cast off in this way will become part of the raw material for future stars and planets. Here, in the near stillness of your own room, it can be quietly comforting to remember that stars, too, go through their late chapters slowly and with a kind of grace. The red giant does not vanish in an instant. It breathes out its outer layers in pulses and waves. The local bubble is carved by a series of events over millions of years, not a single moment. Even at cosmic scales, change comes in long, drawn-out steps. As you drift along this thought path from compact six-star systems to vast glowing cavities, to a single aging giant wrapped in its own dust, the universe begins to feel less like a place of sudden shocks and more like a slow, ongoing unfolding. And somewhere inside that unfolding, your own brief span of days and nights finds its quiet place, resting under the same patient sky. In the deep interior of CW Leonis, the balance between pressure and gravity is no longer calm. The thermonuclear reactions that keep the star shining do not proceed in a smooth way. They stutter and surge. As helium and other elements in the core fuse, the energy flow sometimes drops, letting the star's outer layers cool and sink inward under their own weight. That contraction squeezes and heats the inner regions again until fusion flares up more strongly, pushing the envelope outward once more. In this way, the giant seems to breathe. It swells, cools, and dims, then shrinks, heats, and brightens. For CW Leonis, the full rhythm of this breathing lasts about 649 days. At its brightest, the star shines well over 10,000 times more powerfully than the sun. Even at its faintest, it still outshines our star by several thousand suns. To us, wrapped in dust and distance, those changes are subtle, but to the gas close by, they are a powerful heartbeat. During the phases when the star contracts and its outer layers are tugged more tightly inward, some of that fragile material becomes unstable. Portions of the upper atmosphere detach and drift away, pushed outward by radiation and stellar wind. Over tens of thousands of years, this shedding has built a vast envelope around the star, a cloud of gas and dust, rich in carbon and oxygen. CW Leonis loses an amount of mass each year, roughly comparable to several Earths. The circumstellar nebula that has grown from this loss is thought to be tens of thousands of years old and to contain more mass than the Sun itself, spread out over a region far larger than our solar system. Within that shroud, the material is far from smooth. Observations reveal arcs, clumps, and partial rings, as though shells of gas had been cast off in different directions at different times. Magnetic fields and the uneven pressure of the stellar wind likely sculpt these shapes. Some regions are denser, some thinner, some glow more brightly in certain wavelengths, showing complex flows in the slowly expanding cloud. The chemistry inside this envelope is especially intriguing. When astronomers break its light apart into a spectrum, they find signatures of dozens of different molecules. Alongside simple compounds like carbon monoxide and water vapor, there are traces of ammonia and more complex carbon-bearing species. Heavier elements, forged in earlier stages of the star's life or inherited from the gas that formed it, are present too. The space around CW Leonis becomes a chemical laboratory where dust, grains, and molecules form, break apart, and reform under the quiet influence of radiation and time. It is possible that long ago, when the star was smaller and hotter, planets orbited within what is now its swollen envelope. If they did, they would have been engulfed as the star expanded, their solid surfaces dissolving into the outer layers. Today, careful watching has not revealed clear, surviving worlds. What has appeared instead are hints that something small but significant may still be circling the giant. In the mid-1990 seconds, astronomers noticed tiny irregularities in the motion of the star that suggested it might be gently tugged by an unseen companion. Later, images of the surrounding nebula showed knots and streams of material, as if parts of the cloud were being stirred by a small object moving through it. One possibility is that a dim red dwarf, less massive than the Sun, orbits CW Leonis at a distance where it takes about a century to complete a loop. If such a companion exists, it is difficult to see directly. The thick dust around the red giant scatters and reflects light, hiding fainter sources in its glow. It is like trying to spot a candle flickering behind a swirling veil of smoke. For now, the companion remains hypothetical, inferred from the patterns left in gas and light. Another mystery in the environment of CW Leonis involves water. For a long time, it was assumed that oxygen in the star's outer layers would be almost completely tied up in carbon monoxide, leaving little available to form water vapor. But observations in the late 2000s complicated that picture. Spectral lines of water were measured at temperatures of around 1,000 degrees, far hotter than would be expected if the water were simply coming from evaporating comets in cooler outer layers. The data pointed instead to water vapor forming in much warmer regions closer to the star's surface, where theory had said there should be almost no free oxygen at all. To explain this, astronomers proposed that some of the dust, grains, and molecules in the outer atmosphere, such as those containing silicon and carbon, might be broken apart by ultraviolet radiation. Once those molecules are shattered, the freed oxygen atoms could react with abundant hydrogen to form water, even in very hot gas. The challenge is that in a red giant like CW Leonis, most ultraviolet light from deeper layers should be strongly absorbed before it reaches those heights. One way around this is to imagine that the star's surface is not uniform, because CW Leonis is unstable and convective. Its atmosphere may develop temporary gaps and low-density regions, like thin spots in a cloud. Through these openings, more energetic radiation could leak outward, reaching pockets of gas where it can drive the necessary reactions. Over time, this could create a halo of hot water vapor mixed into the star's surrounding envelope. Even if the total mass of this water is enormous when counted in tons, it is still only a tiny fraction of the star's overall mass, a trace ingredient in a vast recipe. Yet for planets that may one day form from the remnants of such envelopes, these molecules matter. They help seed future clouds and oceans with the ingredients that make chemistry rich and varied. According to our current understanding of stellar evolution, CW Leonis is in the late autumn of its life. The fuel in its core is running low, and the cycles of expansion and contraction will not continue forever. In perhaps 10 to a few tens of thousands of years, a long time for us, a short final chapter for a star, it will shed its outer layers more violently, creating a brighter, more compact nebula. The exposed core will contract into a white dwarf, a small, dense object with a mass not much less than the Sun's, packed into a volume comparable to that of Earth. In the first moments after this transformation, the new white dwarf will be scorching hot, with temperatures of millions of degrees. It will shine fiercely in ultraviolet and X-ray light, illuminating the surrounding shell of gas. Gradually, with no new energy being generated in its core, it will cool and dim. Over billions of years, it will slip from white to red and eventually into darkness, a black dwarf radiating so little that it is nearly indistinguishable from the cold of space itself. The story does not end there, though. During the final shedding of its envelope, in the shock-heated regions around the star, some of the heaviest elements in the periodic table are created or dispersed: gold and lead, uranium, and other radioactive species. These atoms drift out into the galaxy, mixing with the interstellar medium. In some distant future, they may be drawn into new clouds, new stars, and new planets. On those new worlds, long after CW Leonis has passed into silence, the decay of radioactive elements in the depths of young planets can provide heat, driving volcanic activity, melting buried ice, and helping to sustain subsurface oceans in those hidden seas enriched with minerals and warmed from within. Simple chemistry may once again find ways to become life. In that sense, even a dying red giant has a gentle, indirect hand in futures it will never see, contributing quietly to the possibility that somewhere, someday, under another sky, someone will look up and wonder how the story began. The universe is not only a place of quiet drifting and gentle cycles, it also reshapes itself through events that are sudden, fierce, and destructive. Stars are born and die, gas clouds are shredded and rebuilt, and sometimes gravity gathers so much mass into such a small space that something stranger appears, a region where light itself can no longer escape. Out of every storm, new structures eventually emerge, but some of them are among the most mysterious objects we know. Trying to find something that does not let any light out is a difficult task. A perfect black object, by definition, hides from the very tool we most often use to see. That is one reason why the number of firmly identified black holes in our galaxy is still small, even though calculations suggest that the Milky Way should contain many millions of them. Set against the hundreds of billions of stars in our galaxy, even that huge number makes black holes relatively rare. They are scattered through the disk, quiet, unless they have something nearby to disturb. To form a stellar mass black hole, a star at the end of its life must be truly massive. Only when the core of such a star is heavy enough, and the supernova explosion that signals its death is powerful enough, will the collapse continue past all the usual stopping points. Pressures that can support white dwarfs or neutron stars are overwhelmed, and the core contracts until it is confined within a region so small that the escape speed at its surface exceeds the speed of light. The boundary of this region is called the event horizon, and its radius for a non-rotating black hole is often described by the Schwarzschild radius. Beyond that surface, according to our current theories, no signal can return. What the interior of a black hole is really like remains one of the deepest open questions in physics. General relativity suggests a singularity, a place where densities and curvatures of space-time become extreme and our equations break down. Quantum theories hint that the picture must be more subtle. For now, all of those details are hidden from us. We can only study black holes through their gravity at a distance, and through the light and other radiation produced by matter on its way in. One of the closest known examples of such an object to Earth belongs to a system cataloged as A62000, also known as V616 Monocerotis. It lies a few thousand light-years away in the direction of the faint constellation of the Unicorn. To an ordinary telescope, it looks like a single, modest star with a soft orange glow. But careful measurements of its motion reveal that it is actually part of a tight binary, circling an unseen companion. The visible star in this pair is an orange dwarf with about half the mass of the Sunday. It orbits the invisible object in just under 8 hours, tracing a small circle around a shared center of mass. From the way the visible star moves, astronomers can calculate how heavy its partner must be. The answer is several times the mass of the Sun, too massive to be an ordinary white dwarf or a neutron star. The simplest explanation is that the hidden companion is a black hole. The orange dwarf does not simply orbit in peace. The strong gravity of its invisible partner tugs at its outer layers, stretching the star slightly out of shape and drawing gas away. That gas does not fall straight in, but spirals around, forming a flattened, glowing ring known as an accretion disk. As the gas in the disk rubs against itself and moves inward, it heats up to very high temperatures. It is the light from this hot, swirling material, not from the black hole itself, that we detect when we look closely at the system. Around V616 Monocerotis, other stars keep their distance for now. There are dozens within a few light years, and some almost certainly host their own planets. Over very long timescales, though, gravitational nudges can change orbits. It is quite possible that, in the deep future, one of these neighboring stars will wander close enough to be strongly affected by the black hole's pull. If that happens, gas from the new companion may also begin to flow inward, feeding and brightening the accretion disk. How a black hole interacts with nearby objects depends on mass and distance. The stronger the gravity and the closer the companion, the more intense the tidal forces become. These tides can stretch a star into an elongated shape, drawing it out toward the black hole. In more extreme cases, they can tear material away entirely, opening channels through which gas streams toward the disk. If a star or planet strays too close, the difference in gravity between its near and far sides can become so large that it is ripped apart, spread into a glowing arc of debris. Despite their dark reputation, black holes are not vacuum cleaners that swallow everything. From the point of view of gravity at a comfortable distance, a black hole of a given mass behaves much like any other object of the same mass. If you were to replace the Sun with a black hole of equal mass, the planet's orbits, in a purely gravitational sense, would hardly change. They would continue circling as before, though their skies would be very different. This means that, in principle, a black hole can host a system of orbiting planets, asteroids, and comets, just as a normal star does. Such planetary systems could form in several ways. In one scenario, after a massive star explodes, some of the gas and dust left over in the region does not escape entirely. Instead, it remains bound to the new black hole, eventually cooling and collapsing into a disk. Within that disk, clumps of material can gather, collide, and grow, slowly building planets and moons over millions of years. In another scenario, the black hole passes near an existing planetary system. The encounter may tear the original system apart, but some of its planets can be captured into new orbits around the black hole. Over time, the surfaces of such captured worlds would change. A gas giant that loses much of its atmosphere to the intense environment might leave behind a denser core, transformed into a different kind of planet. An ice world that drifts into a region warmed by radiation from an accretion disk could see its frozen crust soften, forming deep oceans. Free-floating planets that once wandered between the stars might also be snared, joining the retinue. We have not yet directly detected a definite planetary system around an isolated black hole, but our current understanding of gravity and planet formation offers no reason to rule them out. They would simply be difficult to find. Any light they reflect would be faint, and any warmth they receive might come more from the glow of hot gas in the disk than from a central star-like source. For planets that move too close to the center, however, the environment turns from strange to lethal. Near an actively feeding black hole, the accretion disk can be very hot, shining in X-rays and other high-energy bands. A planet orbiting within such a region would be bathed in radiation that could strip away its atmosphere. Friction with thin but fast-moving gas could slowly rob it of orbital energy, causing its path to decay. As it spiraled inward, tides would eventually grow so strong that the planet would be stretched and torn apart, its material joining the glowing ring. From far away, such a final fall would appear as a flare, a brief brightening in the light from the disk as new matter is added and spirals down. Then the glow would fade again, leaving only the steady pull of gravity behind. In this way, black holes are both destructive and oddly gentle. They do not seek out matter, but they reshape whatever comes too near, folding it into their own dark story, while the universe around them continues, always, to make new stars, new clouds, and new chances for light. When a planet, a star, or a cloud of gas is torn apart too close to a black hole, its remains do not vanish all at once. The fragments are stretched into long, glowing streams that spiral inward. Bit by bit, they are dragged into the accretion disk, where they are stirred and heated by friction until they melt into the hot, swirling gas. Over time, that gas drifts closer to the event horizon, giving up energy as it goes. In the end, each fragment crosses the boundary where return is no longer possible and, from our point of view, becomes part of the black hole itself. Astronomers usually talk about three broad kinds of black holes, grouped mostly by their mass. The first are the giants that sit in the hearts of most large galaxies. These supermassive black holes weigh as much as millions or even billions of suns. Near the center of a galaxy, matter is crowded. Stars form in great numbers, many of them large and short-lived. As they exhaust their fuel and collapse, some leave behind black holes. Over cosmic time, those remnants can grow by feeding on gas and on one another, merging again and again into a single, enormous object. When there is plenty of material nearby, a supermassive black hole can build a truly vast accretion disk. Gas in that disk orbits at tremendous speeds, heating up to extreme temperatures and shining with incredible power. In some cases, narrow jets of particles are launched from the regions near the black hole's poles, spearing outward for thousands of light years. Seen from far away, these active galactic centers can outshine all the stars in their host galaxy combined. When they are particularly bright and distant, we call them quasars. Some of the quasars we see today are so far away that their light began its journey billions of years ago, when the universe was young. The second main group are stellar mass black holes, the kind formed from individual massive stars at the ends of their lives. Their masses are closer to a few or a few dozen suns. They are much more common than the supermassive ones, but also much harder to find because most of the time they are quiet. Unless they have a companion to feed them, they produce no bright disk, no powerful jets, only gravity. When two of these stellar mass black holes orbit one another and eventually collide, they send out ripples in space-time, gravitational waves that we can now detect with sensitive instruments on Earth. Between these two ranges, astronomers suspect that a middle category exists: intermediate mass black holes, heavier than collapsed stars, but lighter than the monsters in galactic cores. They may form when stellar mass black holes grow by slowly eating gas and stars in dense clusters, or when several of them merge. A few candidates have been found, but their numbers and origins are still being pieced together, like faint constellations slowly emerging from noise. The third kind belongs, for now, mostly to the realm of theory. These are primordial, or primary, black holes, tiny objects that might have formed in the very early universe, long before the first stars. In that distant era, matter and energy were packed more tightly together, and small fluctuations in density could, in principle, have been compressed enough to collapse directly into black holes. If such objects formed with very small masses, our current understanding suggests they would slowly lose energy over time through a quantum process sometimes called evaporation. The lighter they were, the faster they would have faded, ending their lives in brief bursts of high-energy radiation. So far, we have not seen clear evidence of such final flashes, and no primordial black hole has been unambiguously identified. Other ideas explore the possibility of even more exotic versions, microscopic quantum black holes that could, in theory, appear when particles collide at extremely high energies. If they form at all, they would be extraordinarily short-lived, dissolving almost as soon as they appeared. The conditions to create them naturally are thought to have existed mainly in the early universe. In laboratories, our accelerators are still far from those energies, and even there, any such object would vanish too quickly and too subtly for current instruments to catch. Given how dark and compact black holes are, it is no surprise that they are difficult to detect. We usually find them by watching how they affect their surroundings. In some systems, we see a visible star moving on a path that cannot be explained by the gravity of any object we can see. Its orbit loops around an unseen companion whose mass can be inferred from the star's motion. If that mass is too large and too compact to be anything else, we conclude that a black hole is the most likely explanation. In other cases, we focus on the light from accretion disks. Gas spiraling into a black hole produces radiation with characteristic energies and patterns. X-ray telescopes, in particular, can pick out these signatures, distinguishing them from other hot objects in space. With very sharp imaging and clever techniques, astronomers have even managed to reconstruct images in which the bright ring of an accretion flow surrounds a darker central region, not the black hole itself. but its shadow carved out of the light by gravity. There is also a more subtle method called gravitational microlensing. If a massive, unseen object passes almost directly in front of a distant star from our point of view, its gravity can act like a lens, bending and magnifying the star's light for a short time. By watching for these temporary brightenings and analyzing their shapes, astronomers can infer the presence of compact objects that emit no light of their own. This technique is delicate and relies on chance alignments, but it offers one of the few ways to find isolated black holes drifting quietly through the galaxy. Black holes, for all their strangeness, are just one possible ending in the story of a star. Most stars will never collapse that far. Some will gently shed their outer layers and retire as white dwarfs. Some will leave behind neutron stars, tiny, dense spheres that still pulse and spin. Others, the most massive, will fall all the way into darkness. When we study these different paths, we are not only learning about distant objects, we are also tracing the long chain of events that made our own existence possible. The calcium in your bones, the iron in your blood, the oxygen in the air you breathe, all were forged in earlier generations of stars and scattered into space by explosions and winds. Over time, that material gathered again into new clouds, new suns, new planets. On one of those planets, under the light of an ordinary star, life began to stir. Lying here now, listening and breathing, you are part of that unfolding, the atoms that make you once belong to other worlds and other skies. The light that reaches you tonight has crossed vast distances from stars at every stage of their lives, from young blue suns, from quiet red dwarfs, from swollen giants near their end. Somewhere, black holes are quietly bending the paths of that light, shaping the universe in ways you cannot see. And still, on this small world, you have a moment of rest, a tiny, bright pause in a story that began in the hearts of stars and will continue long after their fires have gone out.